Uh, Welcome to the last section of the day one. So we have three speakers for this section. So let's start from the first speaker, Mr. Kevin Yontomyos.
Có cái người đi chỉnh ra để ngồi đã.
Alright, hello everyone. My name is Kevin Yontomyos. I am a PhD student at Chiang Mai University, and I'll be presenting to you today high precision modeling of COVID-19 using SIRDV model with time-varying parameters. So before I get to my own model, I'm going to describe a little bit what an SIR model is. And as you can see here, we have three compartments, S, I, and R, where S stands for susceptible, I stands for infected, and R stands for recovered or removed. Depending on the interpretation of the model, it could either be recovered or dead. So typical SIR models depend on constant parameters such as beta for the transmission rate and gamma for the removal rate from the infected compartment. And the plots here are usually what the numerical solutions of the SIR model look like, which in most cases is fine because diseases come and go, right? People get infected, but eventually, everyone gets affected at some point, and the disease eventually goes away. But that is not always the case. For example, COVID, where we have multiple peaks, right? The disease keeps mutating, and we get more infections every once in a while, and sometimes we get larger peaks, sometimes other times smaller peaks. So this is why I created this model, the SIRDV model, where we have time-varying parameters, where the transmission rate, probability of death, vaccination rate, are allowed to vary with time. So unlike the regular SIR model, they're not kept constant. So here is the system of differential equations that are derived from the model. And as you can see, the terms beta Si over n are the mixing between the susceptible and the infected people in the population, and the term beta Vi over n, the mixing between the infected people and the vaccinated people, meaning that people who are vaccinated can still become infected. And for the differential equations for R and D with respect to time, you could see that the term that is multiplied by I, it's multiplied by a factor of 1 minus P, and P being the probability of dying from COVID-19. So for finding the parameters, we use F-min search, which is a lightweight optimization technique based on the simplex algorithm, where usually if you would use this method, you would perform F-min search on the entire time period and get a set of parameters. But for this model, we perform this optimization parameter estimation technique at every single time step, and we do that by minimizing the sum squared errors, the SSE, between the numerical solution and the real data. So here's an example plot of solutions for the United States. As you can see, well, it's a little light on the screen, but the active cases are able, the solution is able to match the real data very, very well. And the same can be said about the deaths and the vaccinations. And we're able to do that because we vary the parameters of time. And the first plot shows the transmission rate, beta. And you can see that at first, well, it's obviously very high because that's when COVID started. And it dips down because of the lockdown and safety precautions, masks and stuff. And also towards the second half of the time period, you can see that it goes back up because people start to care less, right? And for death rate, at first it was very high, and that's why it was so concerning because a lot of people were dying from COVID-19. But eventually, once vaccines came out, as you can see from the plot of vaccination rates, well, the death rate significantly decreases, although it still has a few spikes here and there because of the new variants. So in the last slide, I showed the plots for solutions for the United States and the parameter values. So, and that was what I did originally. And then I was like, well, maybe we could extend it and apply it to other countries as well. And turns out we can. And as you can see, the solutions for active cases, deaths, and vaccinations are able to match well for not only the United States, but also Japan and Germany. And here's another set where we do Poland, France, and Mexico. Right, all able to match very well with the real data. And here are the parameter values for each country. The first row being the United States, second being Japan, third being Germany. And you can see that they generally follow a very similar trend where the transmission rates for all the countries here, they start off a little bit higher. They dip down for a while, for the first half of the time period at least, and then it spikes back up because people are less careful. So for deaths, same thing. We have a very large initial spike because that is when COVID first came around and lots of people were dying from it. And then eventually we have smaller and smaller spikes, and eventually, like in Japan and Germany, where the spikes get smaller and smaller, and eventually it's like pretty much zero now at this point. Same thing for vaccinations. They pretty much became available at around the same time, so we get to see pretty much one big peak for all three countries at the same time. And then smaller ones as the remaining people are getting vaccinated. Same can be said for Poland, France, and Mexico, where the plots still for transmission rates still observe the same behavior. And next up is reproduction number, where reproduction number, well, first off I should say, basic reproduction number means if one person is infected, how many more people can this person infect? And we define that as the rate entering into the infected compartment over the rate out. So in this case, it would be beta over gamma plus mu, where mu is the natural death rate for reasons other than COVID-19. But you'll see why this is not enough momentarily. So we have to consider the effective reproduction number, where we account for the number of susceptible people over the total population. So here, the plot of basic reproduction numbers, where we don't account for the susceptible population. You can see it only does well in the first half, right? Second half, not so great because it rises up way beyond where it should be according to reported data according to the statistics. And that's why we have to consider the effective reproduction number, where here it's much, much better. And we could see that using our method to compute the effective reproduction number, it agrees well with the reported reproduction rate data by our world in data, where they probably use statistical methods. So next up is sensitivity and elasticity, where sensitivity determines which parameters are most influential to solutions of the model. But the downfall of that is that sensitivity is local and it's not able to account for the wide range of parameters that we're able to use in the model. So we should also consider elasticity. And here are the formulas for sensitivity and elasticity, where we take the partial derivatives of the reproduction number with respect to each parameter, right? But then for elasticity, we do the parameter, and then we multiply it by the parameter over the reproduction number, the effective reproduction number. So first, results for sensitivity, right? At first, it starts off, speaking of magnitude, it's quite high, right? But then eventually, quickly, very quickly, actually, it for every country, it goes to around, I would say, like around -10 on average. But for sensitivity of beta, more interestingly, it actually drops, because as time goes on, less and less people are able to be infected, because not only are a lot of people infected already, right? So if there's a lot of people infected already, there's not going to be much transmission going on. And also vaccinations, if there's a lot of people vaccinated, maybe it'll change. So here are the elasticity values for all 6 countries that we did, where we see that the elasticity of the reproduction number with respect to gamma, the exit rate, are all quite similar, right? But then the elasticity of the reproduction, the effective reproduction number with respect to the natural death rate changes. And I should also note that we use different natural death rates according to each country. So to conclude, advantages, obviously, we're able to match the real data extremely well, right? I would say it's probably very versatile, because we could apply this model to pretty much any infectious disease that we want, assuming that there's a good reason to. The change in behavior of people and in the disease are able to be observed in detail, where otherwise, with constant parameters, we're not able to do that, because if with constant parameters, we just assume that people will and the virus will behave the same way throughout. Disadvantages: data overfitting, of course, because we use so many parameter values when we try to model with such high precision. And also difficulty in forecasting, because as you can see from the parameter values, it's really hard to guess what the parameter values are going to look like next. Unlike if we use constant parameters, we could probably continue using that same parameter and seeing what the solutions are going to look like eventually. That's it for me. Thank you.
Okay, thank you. Is there any question? I wonder, can we use this model to predict the Thailand?
Oh yes, definitely. I actually did actually did predict. Well, actually, I actually did model the spread of COVID-19 for Thailand, but for a different project that is very similar to this one.
All right, thank you.
Yes, thank you.
Okay, all right. Okay, please give him another approach. Thank you very much.
Thank you so much.
Well, so I would like to welcome the